Hello, Assalamu alaikum. Are you all able to hear me?
Yes, miss.
Did you guys attempted the quiz?
Yes.
Yes, miss.
How was it? It was okay?
Yes.
Okay. No, I didn't receive yours.
Miss, I'm on the last question. I'm just gonna send you right now.
Okay.
Yeah.
All right. So let's begin with the topic of metals. We were doing metals, right? Is the screen visible to everybody?
Yes, miss.
All right. So up till yesterday, we have discussed something about the reactivity of the metals, the physical and the chemical properties, some of the reactions that they undergo. And the main reactions that you need to know is you can either jot them down on a piece of paper, just in a comprehensive manner. So to be able to memorize it, and like for instance, if you are looking at it repeatedly, you will be able to get to know the reactions much better. So for instance, we said that metals, when they react with acids, they form salt and hydrogen gas is evolved. I told you that whenever these reactions are asked, they are either going to ask you the products which are formed, they'll ask you to complete the whole chemically balanced equation, and they can also ask you to tell your observations. Okay. Then metals, when they react with oxygen, they form their own oxides. This is an oxidation reaction. Metals reacting with cold water, only those which are very much reactive, produce metal hydroxide and hydrogen is evolved. But the ones which are less reactive, they are not from group 1 to 3. They react with steam and they also produce, as a result of which they produce metal oxide and hydrogen. Okay. So one distinctive property of the aluminum is that it reacts with very readily with the oxygen, the atmospheric oxygen, as a result of which it produces a layer of aluminum oxide surrounding it, thereby apparently showing very decisive nature of the aluminum metal, you can say. That it is, however, very reactive, but it shows or apparently behaves as if it is unreactive. Okay, moving on to the next chemical reactions regarding metals. Still, again, here, what I'm going to ask you guys to remember just the general equations. General equations, if you recall the general equations actively, you will be able to solve any kind of equation with any other metal. Okay, so metal hydroxides or any other metal compounds, they basically also undergo decomposition reactions. Now, what are decomposition reactions? And particularly, they are basically thermal decomposition reactions. Now, as the term suggests, thermal stands for the heat energy, right? And decomposition reaction means that such a chemical reaction, which is whereby a metal compound is going to break down. Okay. So decomposition basically means where a particular reactant is actually breaking down to produce new products, and this is going to take place in the presence of heat energy. So you have to provide certain heat energy source. All right. The more the reactive a metal is going to be, its compounds are also very thermally stable. This means that if a compound is very reactive, okay, you have a compound which is very reactive, this means that it is going to be very thermally stable. And because of its greater thermal stability, this also means that more energy is required to break it down, okay? Or it is going to be very hard to decompose it. So this is only true for the reactive metals. The most reactive metals, they require more energy to decompose, and that is because of greater thermal stability. Metal hydroxides, the first general equation is metal hydroxides, whenever they are thermally decomposed, what do they form? They form metal oxide and water is produced as a result. Sodium and potassium hydroxides, they do not decompose when heated, and this is because of the greatest thermal stability that they have. Moving on to metal nitrates, particularly talking about sodium and potassium nitrate, when they are heated, they produce nitrite and oxygen. Nitrate is NO3 minus, and whereas nitrite is NO2 minus. Okay, so sodium nitrite is formed, which is NaNO2 plus oxygen is produced as a result. Okay, if there is any other metal nitrate other than sodium and potassium, it is going to decompose to form metal oxide first, and then nitrogen dioxide is produced as a result. And nitrogen dioxide is basically brown in color, so brown vapors are seen or observed, and this colorless oxygen gas is also evolved. Okay, remember these general equations, right? I'm repeating myself. Metal hydroxides, when they decompose, they produce metal oxide and water. Sodium and potassium nitrate, when they decompose, they produce nitrite and water, nitrite and oxygen. Nitrite is NO2 minus, nitrate is NO3 minus. Any other metal nitrate, when it decomposes, it produces metal oxide, nitrogen dioxide, and oxygen. Metal carbonates, when they decompose, they produce metal oxide and carbon dioxide is produced. Okay, so remember that carbonates produce or give off carbon dioxide gas, and the rest of the oxygen which is left is going to react with the metal to form metal oxide. All right, up till here, do we have any queries, any questions? Yes, Zoe.
Miss, could you repeat the thing about thermal stability?
About thermal stability, I said that the more reactive the metal is, it is going to form most stable metal compounds. Okay, so supposingly you have a metal which is sodium or potassium. It is in group 1 of the periodic table, and we said that group 1 metals, they are the most reactive out of all the metals. Okay, so group 1 metal compounds which will be formed will be very stable because of their greater reactivity. Okay, and because of this, their compounds, they have greater thermal stability, which means that when you need to decompose them, it would be very hard to decompose. This means that too much of energy is required to decompose them. And specifically talking about metal, uh, what was it? Metal hydroxide, like sodium hydroxide or potassium hydroxide, they are very difficult to decompose. Okay, so the greater the thermal stability means that the metal was too much reactive to form a very stable compound, as a result of which lots and lots of heat energy is required to decompose it or to break it down.
Okay, Miss.
Moving on to galvanizing and sacrificial protection. This is important. Questions, they do appear in exams regarding galvanizing and sacrificial protection. Now, basically, these are two different methods, but they serve the same purpose. Okay, and what is the purpose? The purpose is that the less reactive method is basically protected by or saved by a more reactive method, and this helps the less reactive metal to get corrode away very easily. Okay, so who is helping the less reactive metal? The more reactive metal is actually helping it out. So what happens in this case scenario? And usually what they are going to ask you, they are going to ask you mostly about iron. Iron is a very easily, it is it has greater applications, okay, which is why we are talking about iron metal specifically. Iron, when it reacts with either air or water, it produces its own oxide, metal oxide. Or when air and oxygen, both of them, they are present, it is going to form a compound which is rust, okay. And this rust chemically is known as hydrated iron 3 hydroxide, okay. This is hydrated iron 3 hydroxide. All right. So these salts, they're basically produced. So rust basically has hydrate, or is known as chemically hydrated iron 3 hydroxide. And to prevent iron from rusting, these two methods are used. And these two methods, they basically use the principle of the metal reactivity series, okay, whereby we see that any metals which are actually present above iron in the reactivity series, thereby them being the most reactive or the more reactive metal, they are able to easily save this iron from being corroded away. So what happens in sacrificial protection? You see in this in this diagrammatic representation, it shows that you have a ship hull. Okay, so what happens in seas, that the ships and the larger ships and their ship hulls, they're basically made of, their sides, they are made of steel, okay. And steel has iron and some element of some component of the element carbon, okay. But iron is basically the main primary element which is present within steel. So to prevent that iron from corroding away, these zinc blocks, they are placed just with this hull, okay. And what happens that since these ships, which are used usually for trade routes and so these ships which are basically used for trade routes, they have to be in the sea, as they have to travel the sea route for very long time, even for like months, okay. So so to prevent iron from corroding away, this zinc blocks are placed. Now if you remember, and if you are able to connect this dot, the zinc in the reactivity series is basically present at the top in the reactivity series. It is present above in the reactivity series than iron, which makes zinc the most reactive as compared to iron, which means that zinc is the most reactive metal. So it is going to help protect iron from getting corroded away, which is what makes it this whole process the sacrificial protection. Okay, so sacrificial protection is that the more reactive metal is actually sacrificing itself to protect the less reactive metal. Okay, is this point clear so far? The more reactive metal is getting itself oxidized. So any oxygen or water, whatever it is present, okay, it is going to within the atmosphere and in this within the sea. So it is going to react with the zinc, as a result of which it is going to get itself oxidized. So these zinc blocks, they will be corroded away first as compared to the less reactive metal here in this case scenario, which is iron. Okay, so this method is referred to as sacrificial protection. And obviously these zinc blocks, once they are corroded away, so they need to be repetitively they have to be replaced, okay, once they are all corroded away. So zinc is more reactive than iron, therefore it is going to lose its electron, which means it is going to get itself oxidized more easily as compared to iron. And this is what happens in the sacrificial protection. The half equation that we're going to look into is obviously that zinc is going to lose its electrons, thereby getting itself oxidized to form the oxide, okay, its own oxide. So for continued protection, these zinc bars must be replaced. I just told you. Then the next process is galvanizing. Is this process clear so far?
Yes, miss.
Okay.
Yes, miss.
Moving, all right, moving on to the next one, galvanizing. Galvanizing is a process where the iron is protected, and here you don't use zinc blocks or something. You basically coat the whole iron with a layer of zinc. Okay. Now there are two different methods to use this process. Which two different methods? Either you electroplate the whole iron block with zinc. Okay, so zinc layer is going to be present, and this will be by the process of electroplating. Okay, you have iron, supposedly this is the iron block, and you have to use this process of galvanizing. So either you are going to use the process of electroplating, so that zinc is deposited onto iron and creates a whole layer of zinc around iron, hence protecting it so that it is preventing it from corrosion. The other method, which is particularly galvanizing, is coating it with molten zinc. Okay, so you simply have molten zinc which is present, and you are going to use the block, and you're going to dip that iron block within the molten zinc, so that molten zinc layer will be covered and will be covering this iron block. This method is the dipping of iron block into the molten zinc, thereby again coating iron with a layer of zinc, which is galvanizing. So whenever this, supposedly, even if this coating is damaged, or even this is scratched or something from any part, any area, the other areas, they do have still zinc layer which is present. So as a result of which this iron will not be corroded away. Why? Because the zinc will be present, and zinc has greater tendency or affinity to react with oxygen, thereby the method by which this iron will still be protected will be by the process of sacrificial protection. I'm repeating myself again. I said that supposingly you have this iron block is already coated with the layer of zinc. Okay, and this is the layer of zinc which this iron block is covered from. Okay, covered with. But supposingly, I say that at some part this is scratched or something. So what happens that this, supposingly this part is scratched or it is damaged somehow. So this zinc layer is now not present or only at this particular part. But at the rest of the part, the zinc layer is still present. Okay. So then how this iron will be protected? This iron will be protected then by the method of sacrificial protection. Are we clear? I think
Yes,
someone
miss.
has a question. Yes, Zoya.
Miss, is this the same method applied to the zinc blocks? Because
Yes,
we're
yes,
not
yes.
covering the whole thing.
Yes, exactly. Yeah.
Okay.
Mhm. All right. Moving on to the extraction of the metals now. So okay, let's just do a few questions first, and then we're going to move on to extraction. Then let me just a minute. Let me know if the screen is visible.
Yes.
Yes.
Write your answers in the chat box. All right. The first question here says that the diagram shows the experimental setup a student has used to investigate the composition of air. Now, the student left the apparatus in the laboratory and observed that the water level had risen inside the test tube after 1 week. Okay, so there's a trough of water in which an inverted test tube has been placed, and after a week's time period, this water level has risen after 1 week. Which statement do you think explains why the water level has rose? It has risen up. Is it A, B, C, or D? Nitrogen monoxide was produced, or iron oxide was produced, or sulfur dioxide was produced, or the temperature has risen up, or it has increased, which is why the um, water level has risen. Yes, very good. B is the correct answer. Can someone explain why? Yes, Zoya.
I'm not sure, but I think it's because the oxygen will be dissolved in the water and then this will diffuse to the iron, and iron and oxygen will react to form iron oxide.
Okay, so the oxygen which is present in the air within the test tube, it cannot directly react with the damp iron fiber.
Oh, yes, it can.
It can. So basically, what happens? This is true that iron oxide is produced, and that is rust, which is Fe2O3, and this water level is going to rise up because this iron is going to react with the oxygen which is present within this test tube. Okay. So as it is going to completely react with all the oxygen present within the test tube, after which the sample of air will will not have any further oxygen, as all the oxygen within the test tube has now been reacted with damp iron. Okay. Due to this, the water level is going to, as a result, rise up. Is this point clear? Everybody.
Yes, Miss.
Okay. Moving on. A student observed the reaction between copper to sulfate solution and zinc. Which observations are correct for this reaction? Copper to sulfate reacts with zinc. These are the observations that they see. Which one do you think is the correct answer? Is it A, B, C, or D? You have copper to sulfate and zinc. Is zinc more reactive than copper, or is it less reactive than copper?
More reactive.
Yes, very good. It is more reactive than copper. So this means that more reactive metal, if it is present, it is going to displace the less reactive metal copper within its aqueous solution. So copper to sulfate, when it reacts with zinc, it produces zinc sulfate and copper will be deposited as itself. So what will be your final observations? Yes, D is the right answer. Very good. Yes, Rayan, why do you think D is the right answer?
Because copper to sulfate is a dark blue, so when it reacts to turn lighter blue.
Yes, the copper to sulfate is basically blue in color. Okay. When it is going to react with a more reactive metal, this more reactive metal has a tendency to displace this less reactive metal. Okay. As a result of which this zinc sulfate will be formed. Now, new aqueous solution will be formed, and that is going to be zinc sulfate. Now, either you say that this blue is going to turn colorless, but none of the options say that the solution turns colorless. The only options which do align with our theory is that the solution turns paler blue. All right. This says that the solution stays color stays the same. This is absolutely incorrect. It turns darker blue. No. If more copper ions are present, then only it can turn darker blue. Otherwise, no. The solution is going to turn orange brown. No, this is not at all possible. So either you can simply, if you are sure of absolutely about one particular observation, you can mark your answer to be D. But better off to check the other observation here as well. Sometimes you have two similar options, right? So orange brown residue is formed or it is observed, and this orange brown residue is basically the brown deposits or the residue of copper metal which is formed. This is brown in color, or you're going to mention brown copper deposits which are seen or observed. Okay, so your correct answer here is going to be D. Look at this one. Which is the most reactive metal, and which one do you think is the least reactive metal by looking at these test tubes? I think this is an easy one. Yeah, very good. A is the right answer. Very good. The more the gas bubbles are produced, that is going to be the most reactive. And the one which doesn't have any gas bubbles being produced, this means it is very least reactive. Or the ones which have less gas bubbles being produced, that is also going to be less reactive. Okay, moving on to the next question. A compound Y is being thermally decomposed with carbon using the apparatus below. So compound Y and carbon, they are both heated up within a reaction tube. And then whatever gas is produced as a result. So this means that this compound Y is basically undergoing decomposition. You can also say it is undergoing thermal decomposition. And as a result of which some gas is going to be produced, and then this gas is going to react with lime water. They see or they observe that a brown solid is formed in the reaction tube, and this lime water also turns cloudy. What does this tell you about something? If lime water turns cloudy, what does this indicate? Yes, Rayan.
The gas is carbon dioxide.
Yes, the gas is carbon dioxide. And do you remember which metal compound, when it decomposes, it produces this carbon dioxide? Which metal compound, when undergoes thermal decomposition, produces carbon dioxide? Metal oxide, metal nitrates, or metal carbonates? Yes, Zoya.
Metal carbonates.
Metal carbonates. Okay. So this means that this compound Y is basically some kind of a metal carbonate. We yet don't know which metal carbonate this is. Okay. This is going to react with carbon. We can say that this carbon is going to displace metal, okay, this metal, and will form carbon dioxide as a result, or has greater ability to do this. All right. So in the next one, they say that a brown solid is also formed in the reaction tube. What do you think this could be? There is another possibility in this reaction. The other possibility that could be is that this can also be a metal oxide, which is reacting with carbon. And then this carbon is displacing metal to form Simply the metal deposit. This metal deposit is brown. It is brown in color. Which metal deposits are brown in color? Yes. Which metal deposits are brown in color? Could it be copper? Could it be calcium, magnesium, or sodium? Yes, very good. Copper. Okay. So copper is the correct answer here. Copper to oxide, this is. The other possibility, this is going to align with our answer. That is, this is some kind of a metal oxide which is reacting with carbon to produce carbon dioxide as a result. How do we know that carbon dioxide is being produced? Because lime water is turning cloudy. And this metal deposit which is formed is brown in color, which means this is copper. Colored compounds are formed by transition elements, and these oxides, they are basically usually white in color. They are white oxides. Okay, group 1, group 2 metals, they, whenever they form their own oxides, they are usually white in color, and whenever they will be dissolved in water, they will form colorless solutions. They are going to form colorless solutions. So this is going to be copper 2 oxide. And one more thing that you can also depict from this particular reaction, that is copper, this metal has to be less reactive than carbon, because then only this carbon is going to displace this metal. All right. If you have calcium, magnesium, and sodium, all of these, they are more reactive than carbon. They cannot be displaced by the carbon. Is this point clear so far? Yes. Okay. So this is how you basically decode and deconstruct questions. When you're solving one particular question, there should be lots of things which are going through your mind, and you have to eliminate them one by one to get to the final answer. Okay. Moving on, look at this question here. Calcium, copper, and iron and magnesium, they are metals. They can be placed in order of reactivity. Which of the following statements about these metals is correct? Yes, C is the right answer. Very good, Zoya. Why do you think C is the right answer?
Because magnesium and calcium can react with water, and if you see the other options, it's saying iron, like magnesium does not react with steam, which is incorrect, and copper is,
Magnesium does not react with steam?
no, magnesium does react with
Yes.
steam.
Magnesium does react with steam. It has a slow reaction with cold water, but has a rapid reaction with steam to produce magnesium oxide and hydrogen. Carry on.
Okay, and in option B, copper reacting with hydrochloric acid does not form copper chloride because it is less reactive than hydrogen. Copper is less
Yes, very
reactive.
good, very good.
And then the last one, iron oxide cannot be reduced by carbon, which is wrong because
Yeah.
carbon is more reactive than iron.
It says that iron to oxide cannot be reduced. So this is incorrect. Iron to oxide can be reduced by heating strongly with carbon. Okay, carbon is more reactive than iron. It can reduce iron to oxide into iron simply when it reacts with carbon and under presence of heat, okay, or strong heat. So carbon is more reactive. It can reduce iron to oxide to form iron. So the correct answer in this case scenario is going to be C here. Okay. I'm looking for some. Yes, look at this question here. Small blocks of zinc, they are attached to ship hulls, which are commonly made from steel and an alloy of iron. Okay, this is done to prevent the hull from rusting. Which statement explains this process? Okay, Zoya and Ayan, they're saying C. Yes, C is the right answer. Zinc is basically higher up in the reactivity series than iron. Yes, very good, Ayla. So, which is why it has a greater tendency to become oxidized. Any particular metal which is higher up in the reactivity series, which is present above in the reactivity series, has greater tendency to get itself oxidized and will lose its electron. So to give away those electrons to the less reactive metal, which is down below in the reactivity series. You can also see this in some other ways. Like for example, you have some you have two different electrodes, for example, okay? And these are your two different electrodes. Both of them, they are reactive metals, all right? And they're dipped within the electrolyte, right? You don't know what is the power supply. And I say that this is magnesium metal and this is zinc, supposedly, okay? Can someone tell me where will be the electron flow from? From magnesium to zinc or from zinc to magnesium? If you are able to answer these type of questions, then this means that you have had a broader horizon. You are able to
From
link two different topics. Yes.
magnesium to zinc,
From magnesium to zinc. Why?
because it's from positive to negative and magnesium is positive.
Zinc is not positive.
It is positive.
So how will you get to know which one is more positive, which one is less positive?
The oxidation state.
The oxidation state. So magnesium is 2 plus, zinc is also 2 plus.
Then we use the
Which one is more reactive?
magnesium.
Magnesium. Zinc is less reactive. This means that the more reactive the metal is, it has greater tendency to lose electrons or to gain electrons. The one which is
Lose
more reactive,
electrons.
yeah, it is going to lose electron. So magnesium tends to lose electron, get itself oxidized. So it is going to, the electron flow is going to be from magnesium to zinc because of its greater reactivity than zinc. Okay, it is going to be getting itself oxidized and will make zinc reduce. This means that magnesium will lose electrons and zinc will be gaining those electrons. So if this is the case scenario, this means that your electron flow is going to be from this to this. Okay, magnesium will be donating electrons since it is more reactive metal. Okay, this is the most reactive metal and this is going to be your less reactive metal. This is only for those case scenarios where you don't know what the power supply is and you have on both the electrodes you have more reactive metal. Okay, very good. Yes, Ayan, magnesium has higher reactivity than zinc. All right, moving on. Moving to the extraction of metals now. So as we've discussed earlier that the extraction of the metals also depends upon the reactivity of these metals. The more reactive the metals are going to be, they will be found as certain ores. and they need to be extracted using the process of electrolysis of their molten compound forms. Okay, usually they're molten forms of ores, and this electrolysis process is actually very expensive. It is costly, as lots and lots of amount of heat energy is required to extract them. So this is the first category that you have these group 1, group 2, group 3 metals, which are all present above carbon in the reactivity series. They have to be extracted using the process of electrolysis. And one such of it we have done, that is aluminum oxide. What is the name of the ore of aluminum oxide?
Bauxite.
Bauxite. Very good. Yes. So aluminum oxide basically is its ore's name is bauxite, and this bauxite ore has other elements. It has sand as well, which is present, and all of these, they are removed first, and then this main ore, the primary main ore, is basically collected, and this ore is then going to undergo the process of electrolysis. Any elements with metals which are present below carbon in the reactivity series, they can be extracted either by heating them with carbon or any other reducing agent. Carbon basically acts as a reducing agent here. Carbon monoxide is also a very good reducing agent. So either you place this metal oxide within a crucible along with carbon, or in a blast furnace with carbon, and then carbon monoxide is produced, and this carbon monoxide acts as a good reducing agent. Reducing agents are those agents which get themselves oxidized, and they help reduce this metal oxide to form metal. Okay, they steal away its oxygen. So reducing agent is going to steal away the oxygen. And which ones are the reducing agent? Here in this case scenario, carbon and carbon monoxide that we're talking about. So this process is very cheap, and those which are very least reactive metals, they are very naive. They are simply easily found as their own elemental states. Okay. Then extraction of iron. This is very important. In iron extraction, this is the blast furnace in which the whole process is carried out. This is an industrial process. In this particular case scenario, what happens? The name of the iron ore is hematite, and this hematite has primarily it has Fe2O3, okay, which is iron 3 oxide. So this iron 3 oxide is going to be added within this blast furnace along with coke, which is carbon, and limestone, which is calcium carbonate. Okay, so calcium carbonate is actually limestone. Now, once this is added, there are 3 different zones within the blast furnace. The first zone has the highest temperature. Okay, the first reaction that takes place here is that hot air is blown at the bottom of the blast furnace, and this air then rises up. Now, this zone 1 has the greatest temperature. Okay, this hot air containing oxygen is going to react with carbon, which is coke, to form carbon dioxide. This is the first step which takes place. After which, this carbon dioxide is going to then rise up in zone 2, which is having less temperature as compared to zone 1. And then this carbon dioxide again reacts with further coke to produce carbon monoxide. Now, this carbon monoxide, which is produced as a result, basically behaves as a very good reducing agent. Now, this carbon monoxide, which is produced, has the main part here. This carbon dioxide is going to react with Fe2O3 to produce iron and carbon dioxide again. Okay, so this iron is then in molten form, as a result of which this is going to trickle down this blast furnace and will be collected at the bottommost of the blast furnace. After which it is distilled off, it is tapped down, and any of the waste gases, what waste gases? The carbon dioxide. They are going to leave through these vents or the outlets which are present at the topmost. Okay. Now, why is the calcium carbonate present here? This calcium carbonate which is present here is going to react with silicon oxide, okay, as a result of which it is going to produce calcium silicate. Okay. And this calcium silicate, which is CaSiO3, is going to, this calcium carbonate first needs to, the other process that is going to take place is, because of too much of higher temperatures which are present within the blast furnace, this is going to thermally decompose to form calcium oxide and carbon dioxide. This calcium oxide is going to react with silicon dioxide, SiO2, and this only produces one sole product, and that is CaSiO3, which is calcium silicate or slag. This is molten in nature. It is liquid phase slag, which is obviously again going to trickle down and then will be collected at the bottom of the blast furnace, and then it is also going to be tapped. So this is how the impurities which are present within the iron ore, they are going to be collected as slag, molten slag, and finally you're going to extract the metal, which is iron. Okay. Any questions up till here so far?
No.
Okay. One more thing which is also asked here. These reactions, they are interconnected with the chemical energetics as well. Why and how? You should know that when carbon reacts with oxygen and it produces this carbon monoxide, this reaction is basically exothermic in nature. It is going to produce more and more heat energy, which is going to make the furnace very, very hot. It is going to create too much of heat energy. This heat energy will be used up. Okay. This is used up for this reaction of thermal decomposition of calcium carbonate. And if someone remembers from chemical energetics, I told you that thermal decomposition reactions, they are all endothermic in nature. They are all endothermic in nature. Okay. So these steps you have to learn. In zone 1, you have carbon reacting with oxygen to produce carbon dioxide. This is exothermic in process. Then carbon monoxide is produced when carbon reacts with carbon dioxide. Carbon monoxide acts as a very good reducing agent. Then this iron 3 oxide, which is the primary ore of iron, and is going to react with carbon monoxide to produce iron and carbon dioxide. Carbon dioxide is going to leave through the outlets, and this iron will be trickled down, will be tapped off, will be collected. The remaining calcium oxide, which is still present, is going to react with silicon dioxide from the impurity in the iron ore and will form calcium silicate, or also known as molten slag, which is going to be tapped off separately, will be collected at the bottom of the blast furnace. Okay. This is the electrolysis process of aluminum oxide. I think you must remember this. Lastly, we have uses of metals. Metals, they have different uses. You should remember this. This is very factual data. Copper, for instance, is used, is very soft, is easily bent. It is a good conductor of electricity, and it is used in electrical wiring in bases of the pans, because as it is a good conductor of electricity and also heat. Okay. Zinc is used in making of brass. Brass is basically copper and zinc. It is an alloy of copper and zinc is also used in sacrificial protection and galvanizing. Right. Then you have aluminum. Aluminum is basically, it has good tensile strength, so it is used in aircrafts, and also because of its another property of having less density, so which is why it is used in aircraft. And since aluminum has this property of forming aluminum oxide layer, so it is used in food wraps or in any containers wherever food can be preserved. So it's because it is corrosion resistance. Okay, it is corrosion resistant. Then you have mild steel and stainless steel. In the next session, we are going to discuss more about this mild steel and stainless steel, how steel is produced. Mild steel is basically tough. It is ductile, it is malleable, and it also has a good tensile strength. It's basically used in car bodies and machinery. Mild steel actually has iron and 0.3% carbon. Stainless steel has iron, nickel, and chromium. This is an iron alloy having nickel and chromium in it. It is very resistant to corrosion, so it is used in stainless steel cutlery, in chemical plants, and in also surgical equipments. Okay. Any questions by far?
No.
All right. I will be ending the session till here for now. Inshallah, tomorrow we will have a class. Please mention your attendance in the chat box and then you will.
Thank you, Ms. Allah
Thank
Hafiz.
you. Hafiz, Hafiz.
Allah Hafiz, Miss.
Hafiz, Hafiz.